Hi, my name is Jim, and today I'd like to flesh out differential amplifiers a little bit more. And you see on the first schematic here, differential amplifier performance is quite good if certain criteria are met. And do notice the relationship. R1 has to be equal to R2 and R3 has to be equal to R4 for this to function as a true differential amplifier. Now the problem with it is the input resistance of the inverting and non-inverting. So if we take a look at this guy, this is the non-inverting input. Vy is always going to see a constant resistance here, which in this case is just going to be R2 plus R4. Now the inverting input, this is quite different, and what we have here is its node voltage of V prime Y is basically going to determine what this source sees at this. Now what you absolutely have to recall is that there's a virtual short between this if the op-amp is operating in the linear mode. So as this voltage follows this voltage, the current flowing through this can vary. As a matter of fact, it can actually reverse. And I've shown these as AC sources, and then a little bit later we'll explore this with DC. So the way we found the gain of this before is we found the voltage at Y prime and using voltage divider, and then transferred that up to here and found the currents flowing through this resistor, pushed them through R3, and in the case of DC we were very careful to note polarities, and then added this voltage drop to this voltage to find V out. Now, as it turns out, that's a very good exercise in pushing currents, finding out in that method what the gain would be. But there's a simpler method for a DA which meets this criteria, and that is that V out is going to be equal to a negative R3 divided by R1 times the difference between the input Vx and Vy. So do note that the first variable here, Vx, connects to the inverting input. That's very important. And we can collapse this a little bit by saying that we have Vxy, V sub xy, times the negative ratio of R3 over R1. And what you need to recall is this decomposes. It's a doubly subscripted variable, and it decomposes into Vx minus Vy. So given that, what can actually effectively destroy the differential characteristics of this are the impedance of the sources. If they're not zero, Vx can have a varying drop outside of the resistor depending upon the instantaneous voltage of V prime Y. So the total purpose of a DA in many cases is to amplify the difference between the input and not amplify the common component between the input. And that property, called the common mode rejection ratio, is severely compromised under the situation that we have a real source out here. So if we take a look at this specifically to see exactly how bad this can be, and what I'm using here is Y prime. I've not bothered to include the resistors in the circuit, just saying that's the voltage of interest. I'm letting the source be 2 volts with an input resistance to the non-inverting input of 1K. So if Y prime equals 0 volts, due to the nature of virtual short, that means that this node right here is 0 volts. So what we have is 2 minus 0 divided by 1K. So our input resistance, if we work out Ohm's law with that, straightforward, is simply the 1K resistor. It'd just be like having 2 volts and this side of 1K is connected to ground, because if it's 0 volts, ground or not, it's a virtual ground. Now if we let Y prime equal 2 volts, so if we have 2 volts here, is what we see is 2 volts minus 2 volts would be the voltage drop across the resistor, equals 0 volts. And under this circumstance, the input resistance approaches infinity. there's no current flowing. If we let y prime equals 4 volts, then we have a situation of current flowing backward through this. So we have 2 volts minus a negative 4 volts. So the direction of current will be back through this resistor, and under that circumstances, is it a negative resistance? And it's physically positive, of course. Negative resistance is typically in effect, but the current is reversed in this. So this supply would have to be able to deal with that. Now, if current's flowing into this and it's not a rechargeable battery, not a good thing. Finally, if y prime equals negative 2 volts, that would be 4 volts across this. Drop would be plus to minus. We would have 4 milliamperes flowing, and the resistance would end up looking like 500 ohms. So what we can see here is that the input resistance of this leg varies tremendously, and it's a function of this voltage. That's not really a good thing. So yeah, here's the calculations for that to 500 ohms. 2 volts minus a negative 2 volts. 4 volts divided by 1K equals 4 milliamperes. And that 4 milliamperes is flowing through 2 volts divided by 4 milliamperes gives us an effective resistance of 500 ohms. So the part itself doesn't change. It's always 1K. It's what it looks like from the standpoint of the source looking in. Okay, we have another issue here, and that has to do with resistance tolerances. So I've assigned values here to these resistors. These two are equal, and these two are equal. And if we let the tolerance be plus 5%, and what I've done is I've chosen 5% in the worst possible way, where this is 10.5K, 9.5K, 0.95K, and 1.05K. That'll give us the greatest error. Now, with these resistors, typically, if they're 5%, it wouldn't end up being like this. It'd probably be less than 5% and closer together. But when you're designing stuff, you need to do a worst-case analysis, and that's what this is. It's letting this be the worst it can possibly be. So what we have here is, if everything is proper, 10 volts and 1K, our output is going to be negative 10 volts, as we would expect, because the gain of this circuit would be negative 10K divided by 1K. And what we see for the common mode voltage in the output is negative 36.4 nanovolts, and realistically that may be due to features inside the op amp. Now, I'm using a virtual op amp for this. It's not a 741 or any other standard number. Virtual simply means that it behaves like an op amp, and I don't have to deal with power supply rails and so on and so forth. Now, if I take a look at the differential output with the resistor tolerances, 5% in the worst possible way, is I see that the differential gain is now negative 10.9. And what's worse is that the output common mode, and that would be with this source acting and this source being 0, is a whopping 200 millivolts. So that's very significant. The gain is off a lot, and the common mode voltage is significantly higher than what it should be, which is ideally 0. So let's take a look at the common mode rejection ratio with this, and we'll start out with the tolerance of 5% first. I've got the absolute value signs in here because the rejection ratio is a positive number. And to start with, it's simply the output differential voltage component divided by the common mode output component, which is basically equal to A diff, the gain of the differential mode connection, divided by the gain of the common mode connection, except the actual measured value includes the error. This, well, if we're working this off the intrinsic values of the blue up here, the ideal, then this will be off. So if I take my negative 10.9 and divide it by 200 millivolts, what I get for the ratio in the linear domain is 54.5, and then converting that into log domain, which is typically the way common mode rejection ratio is defined, is it comes out to be a horrible 34.73 dB. Now, using the ideal, which is in blue, the actual values, and running the same equation, the common mode rejection ratio here comes out to be 289 million. And converting that into decibels gives a huge 169 dB. Now, this and this are not practical values. A good differential amplifier can hit 100 dB for the common mode rejection ratio, and as the frequency increases, that number decreases, because now, in addition to things like tolerance, is we have variations in stray capacity. So the amp I've chosen here, being virtual, basically comes out to be much better than it would be in real life. Now, what does this have to do with anything really? Who cares if the ratio is great? And the example I offer you is if somebody's in an operating room and they're doing an EKG to find out if somebody's heart is beating properly, and they have, I believe, 5 different probes they put on them, one being on the ankle. They're looking for a very small voltage, which is what causes your heart to beat, and they're in a room which is surrounded, like this room, with commercial power, maybe laying on a metal table, who knows. So there's a lot of common mode voltage potential which is available to it, and these radiate a lot. I have a sensitive radio here, and if I want to listen to anything out of town on shortwave or AM, I have to turn the lights off. Now, these are CFLs, so they have ballast type of circuitry in them and so forth. So under that circumstance, where you're dealing with a very small differential voltage and a very large common mode voltage, is the common mode rejection ratio is the parameter that makes or breaks the whole thing. And that's why, for that example, it really, really needs to be a good number. Now let's take a look at a better circuit, and it's better because it doesn't have a dynamic input resistance anywhere. So this is basically the core of what's called an instrumentation amplifier, which is designed to have very good characteristics. And on some of these, the only resistor that you have access to is the gain setting resistor, RX. Everything else is inside and trimmed carefully. So what we see here is the input resistance of the X input would simply be this resistor, and the input resistance of the Y would be this resistor. And I'm showing these for bias current return to ground. Obviously, it's important that these be as matched as best they can be. And then what we see from this is we are operating these two guys in sort of a voltage follower circuitry, which in turn feeds, guess what? The circuit that we had on the front page. Now, the reason this circuit is okay is because the output impedance of this amplifier with feedback is very, very low. So this is perfectly fine to locate it here. And one other thing, I guess, with regard to this, let me go back a page here. Yeah, right back to here. If you're designing one of these, and in discrete, and you want to know what tolerance the resistor should be, you can use this diagram, substitute in your resistors with the worst case tolerance, for example 1%. So this would be 10.01 k ohms. And then find out, based on a quality, using virtual here, operational amplifier is what the common mode rejection ratio will be. And if that isn't good enough, if 1% isn't good enough, you may have to go down to 0.1%. Now these resistors are available, but as you can probably guess, as the tolerance gets better and better, the cost goes up. Designed the product a number of years ago, and I spec these at 0.1%, and then the people that put the board together put in 5%, and it was being fed by a dynamic microphone, which is typically a low-level output, and in addition to that, this had noise canceling, which makes it a little bit lower, and the hum was very noticeable, and we were using a wall supply with plenty of filtering. So just the shielded coaxial cable, this was twisted pair shielded, had enough ingress so you could actually hear a hum. And when I say hum, I'm referring to either 60 Hertz power line or possibly 120 Hertz, based on the fact that we have rectifiers and things like that, bridges for example, that do have 120 Hertz output as their fundamental frequency. So that's a quick overview on this, and do notice that if you are working with these instead of, oops, I'll go back one more here, if I can do it. Almost. Instead of finding VY to figure out what the total gain is you have this nice compact formula that works just fine. It's just that this criteria has to be met. So that'll conclude on differential amplifiers, and thank you for watching.